shortly. I want to welcome you, first of all, to the first in the series of seminars here in SI 4000. Is everybody here in the SI 4000, or are some from other classes? Did Rudy send anybody over, for example? Okay, just checking. So today we have with us Dr. Len Losik, and he is currently the President and Chief Technology Officer of Failure Analysis, and he's going to talk to you a little bit about that during this presentation. He has over 30 years' experience in the design, manufacture, and testing of military, NASA, and commercial satellites and ground stations that support those satellites. Very wide experience, and has worked for a number of companies, some of the big guys like Boeing and Lockheed Martin, United Technologies, and others. There's a lot more to say about his background, but it's interesting to note in the conversation that we had that his concentration now on this technology of failure analysis is quite interesting. The Navy is finally getting on board with something called condition-based maintenance. Does any of that does that ring a bell with anybody in here? Condition-based maintenance. Okay, so preventive maintenance you know about because the ship comes in for overhaul after a number of years, and you start ripping out pumps and ripping out this and ripping out that because it's time to replace these items. So having come from a shipyard, I can tell you that sometimes we do more damage trying to repair the ship than the ship had when it came in. Condition-based maintenance is an entirely different approach where rather than do preventive maintenance where you periodically replace something, condition-based maintenance says you look at that particular item, you monitor that item, and you replace it only when it needs to be replaced. The Navy is not only going that way, the Air Force is also going that way, and Dr. Losik pointed out that the F-35, is it?
Yes.
Is going to be a condition-maintained aircraft. So failure analysis feeds right into condition-based maintenance, and he can talk to you a little bit about that. Okay, so Dr. Losik has also written and published over 40 books, and he's going to give you a list of those so you can go right on Amazon.com and start buying them. And he received his bachelor's degree in physics and math from San Jose, and also got a master's degree in electrical engineering from San Jose, and his Ph.D. in electrical engineering from Belmont University. So without further ado, Dr. Losik.
Thank you very much. Thank you all for coming. Hopefully I can keep you awake. What he was saying earlier about condition-based maintenance, it's a small segment of a larger program called the Integrated Vehicle Health Management Program. And part of that is using predictive algorithms, much like when you go on the internet and you buy some books at Amazon.com and you come back and then they tell you, hey, based on what you bought last time, you might like these kind of books. That same kind of idea, we're now using that in measuring equipment usable life, electrical and mechanical equipment remaining usable life, so that only the equipment that's going to be failing gets replaced. Not the stuff that's just working fine, may last 10 or 20 years. The equipment will now tell the maintenance people when it needs to be replaced automatically. I mentioned the F-35, which will be flying on Navy ships. By the time the pilot lands the aircraft on a Navy ship, the aircraft will have already downloaded and communicated with the maintenance crew, telling the maintenance crew exactly what equipment needs to be replaced, exactly what maintenance needs to be done, and nothing else will be done. It is what we believe allowed the F-35 to be the first fighter jet program to be funded during peacetime, right? When we didn't have an acknowledged enemy. And the reason that it was funded is because of the 60% reduction in life cycle costs from using a condition-based maintenance program over the 30-year expected life of the aircraft. As a result of that lower life cycle cost of the F-35, they're now backfitting existing fighters, the F-18s, the F-22s, the F-15s, on their high wear-out mechanisms with the embedded these predictive algorithms to measure the usable life on that high wear-out system. So the cost savings are so great by going to a condition-based maintenance program, they're even trying to backfit it on the existing aircraft. Yes, sir?
Have the pilots removed from the
for maintenance. It's all done automatically by the equipment, not by software. There's not an overall monitoring system. Each unit has embedded in it the algorithm that measures its usable life, and that data is sent out to the software for downlinking. So it's not that there's an external software system doing it. It's being done internally on either the electrical equipment or the mechanical equipment. Now, to talk about what I was here for is systems engineering, the methodology, why it is that it came about, and why it's important. And my facts may differ from yours, and so I hope you realize that if I'm saying something that you've heard differently, that you'll just let it go and just recognize that we have different references probably, and so that our facts may be different. And so in 1950 ICBM era, the government recognized that the private industry was driving technology. The Army Air Force, as it was known at that time, was the customer, but the technology was owned pretty much, the smarts was at the companies that were producing this stuff. And they realized that with the ICBM era, with the development of the nuclear bomb, those kinds of things, there were going to be more of those complex systems, and they needed a tool to take the technology away from the companies like General Dynamics, trying to think, Martin of Lockheed Martin fame. Martin used to be Martin Marietta. Marietta used to be part of that conglomerate of companies. And what the government developed was the systems engineering method. And using the systems engineering method, they were allowed to take control of the procurement of these the future large complex systems that we now know today as ICBMs and rockets and satellites and the space station, those kind of big things. In the space industry, same thing happened in the Navy. It allowed the officers, the military guys, to own the technology rather than having to rely on the contractors to drive the programs. And it just so happens that the F-35, the technology, the condition-based maintenance program I was just talking about, the F-35 program is still driven by the contractor Lockheed Martin because the military is so unfamiliar with the technology. So it still does happen where the companies have control of the program, but it's far fewer than it used to be back in the 50s and 60s. And so the term systems engineering was coined as far back as the 1940s, by Bell Laboratories, and the adoption of the systems engineering as a discipline was by DoD and NASA and other industries, including the insurance industry, that was insuring some of these big programs, some of these ships and things, because they needed some standard method for the companies to use when they were building very large, complex things, because it increased reliability. If everybody was doing things kind of the same way, the different companies, you kind of got a standard process, and they felt confident in coming up with insurance premiums. So what's a systems engineer? The term is applied, meant to be used in an interdisciplinary, many different fields of engineering focus on the method of designing and building complex engineering projects. And they worry in the systems engineering method about how they're designed and how they're going to be managed over their lifetimes. And they can be 20 years, they could be 5 years, they could be 20 years, 25 or 30 years. So the systems engineer deals with work processes, it deals with the tools, the documentation, which is really the most important part of the systems engineering method, is the documentation to minimize risk on large projects, and it can also be done on small projects. But it also includes both technical and any human-centered activities, including things like control engineering, industrial engineering, stuff like that. It can be mechanical, electrical as well. And so what is the systems engineering method? And I want to differentiate that from the systems engineering process, and I'm going to cover the process in a little bit. The systems engineering method is this standardized approach of designing and building and manufacturing very large, complex equipment. It's what I like to call once you see it, it'll be kind of an intuitive approach that should, as you're doing it, it should flow naturally. That is, in order to get to the end, the steps that you use in the middle will make sense why they're there. And so it allows, the method itself allows the identification and includes all the documentation and the traceability, which comes as part of the documentation of all requirements. And when something is built, it's built using the requirements that fall out of the systems engineering method. Really, the whole method was designed to come up with the requirements and document them and trace them, so that later on, after all the guys have gone on 5 or 10 years, they've moved on to other things, the folks that are around can still find out, hey, who decided to make it this big? Why did they decide to make it this big versus this size? And so that documentation allows, and that traceability allows all those questions to be asked on very large, complex systems that are around for a long time. So let me say this. It's used by both the customer, which often is the government, the military, and any branch, but it can also be, it's also used by the contractor quite often, and the customer or the government often likes to see their companies that they work with to know the systems engineering method. It gives them great confidence that they share a lot in common. But most companies that produce, actually physically manufacture something like ships or launch vehicles or things like that, satellites, the manufacturing facility itself, those group of people, aren't usually systems engineers familiar with the systems engineering method. The people that actually bend metal don't want to have anything to do generally with the systems engineering method. That's a paper pushing function. And so they don't like to do that, and they don't mix well. Now, everybody knows about fractals, heard about fractals in the mathematics, where the size of or the shape of the object is how it's composed. In mathematics, a fractal is a complex geometric pattern that exhibits a self-similarity in both small details and large details. Well, this is in mathematics using the geometric pattern, but in the procurement of complex systems, this procurement process, the systems engineering method, also has fractal properties, because you can use the exact same process on the smallest project as well as the largest project. And the largest project or system is made up of a lot of smaller systems. You can use this method on all of them exactly the same way. And I'll show you a picture of that later on, how that works. So the systems engineering method that I used 30 years ago to design a bunch of equipment for the space program for the Air Force, this was some of the things that these are the actions that I used that are all part of the standard systems engineering method. And so, first of all, somebody comes up with an idea or a need. In the case of the Navy, some destroyer that's got to be able to survive some new weapon. That would be a need. And so the first thing that's got to be done is, hey, is it feasible to build it? And so part of the systems engineering method is say, you got to do a feasibility study. Let's verify that with today's technology, tools, education, blah, 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 we can actually do it. Okay, so assuming that the feasibility study says, yes, it's feasible, then the next thing is got to be written, has got to be a concept of operations. How do you use it? It takes somebody to define the concept of operations, how it's going to be used, because that's what's going to drive the requirements. How you use whatever it is it's going to be. If it's going to be a ship, how are you going to use it? If it's going to be an airplane, is it going to be flying in the desert? Because if you've got aircraft flying in the desert, you've got different requirements than an aircraft flying off of ships. Because sand comes in and it's a different requirement. So in the concept of operations, it's got to define exactly how it's going to be used in all areas. If it's not covered in the concept of operations, it doesn't get covered in the requirements, and so the contractor can't be held liable for requirements that don't fall out of the concept of operations. So in a concept of operations, you'll often do a Phase A study, which we call like an very high level study. Phase A, we use that terminology to mean a very top level kind of discussion. And you might do a Phase B, but you don't have to. But a Phase B study could be done. And then you go down to the next level of detail in terms of understanding the system definition. And then from there, under after the concept of operations has been done, and you've done this kind of a top-level description of the way the thing's going to be, then you can start doing your requirements generation, and then you have to begin, after you, the requirements include things like your functional, what functions are going to be done? How well do things need to be done? That's under performance, how well things need to be done. And then, are there going to be mechanical electrical interfaces? Those have to be specified if there is. Those fall under interface requirements. Is there going to be a mission life or a usable life requirement? Does the equipment have to work for so long? Talking with the reliability folks here at NPS, they tell me that once somebody's been ordered to get up and start marching to war, the biggest problem that they have is as soon as they start turning on the equipment to start driving and moving ahead, there's this return rate of equipment that fails prematurely. And it turns out there's something like a 27-hour requirement that equipment is supposed to function before it needs to be serviced for the first time. And according to the folks that I've talked to here at NPS, no company has ever met the 27-hour requirement yet on equipment once the military starts marching on getting this barrage of returned equipment that fails prematurely. And so if there is indeed a mission life or a usable life requirement, that has to be met. The testing requirements, any kind of integration. If there's a life cycle in the system, the cost may be a requirement. The schedule may be a requirement, may or may not. But these are the kind of things that come out of the generation of requirements. But another part of the requirements is the allocating the requirements to the specific equipment. In the case of a very complex system, let's see if I can come up with a complex system to look at. This is a picture of showing a complex system of space equipment, as well as ground equipment, as well as users in here. When you come up with a complex system, if this is a system that's to be designed and built, you have to allocate the requirements to the spacecraft, or to the ground equipment, or to the user, or you have to actually specify what each of the segments, when you allocate the requirements, either to hardware or software, to the different segments. And if you've got a complex system, you could have segments. In the case of space, we often have the space segment, we got the ground segment, we got the user segment, the people that are actually going to use the equipment. And likewise, I'm sure in the Navy too, when you're going to have ships, you're going to have logistics that you've got to worry about, maintainability, serviceability, all those kinds of things. And you have to allocate who's going to be doing what and when. And that falls out in the allocation of requirements. So in the requirements documentation part, there's something that we call the requirements matrix, which is a definition, which is a line-by-line item of every single requirement about the system, defined in the requirements matrix. And in that matrix, it will identify exactly where you go to in the documentation that will define what the requirement is, where it comes from, and what other things that it may affect. Very important. And then also there'll be the generation of specifications, an A or a B level spec. Sorry, looks like my laser has lased out. And then a C-spec, we used to use that for the software specification. Now in terms of schedule, has got to be generated as part of the systems engineering method, and you'd want to define if there's any critical paths. That is there any hardware, is there any parts of the system that is, if it doesn't come about on time, is going to stop everything from occurring, from making any progress. And that's what we call a critical path. Those items are defined as part of this method, and the critical paths are defined. Then if the go-ahead of the contract, if there's a go-ahead on the contract, you have your design reviews next, and an SRR is what might be called a system requirements review. Before you actually do a preliminary design review, you'll get together maybe with your contractors and verify that the requirements he's working to are the same ones that you're working to. And the systems requirements review provides an opportunity to do that. And it has been found quite often that the customer and the contractor aren't using the same requirements to work off of. That's why that had to come about. So in the first design review, it's a preliminary design review, And this will be where your contractor has done a fairly mature design that says, hey, I'm ready to go to town. And then the critical design review is really one that says, past this point, there can be no more changes. So the critical design review is very important to the contractor, and he's looking for late inputs from the customer who's ever buying it. And then if you might have a final design review as well. If the customer was actually able to convince the contractor to do more changes after the critical design review, you could have a final design review going over making sure that everything's being done. And again, it's one more opportunity for the customer to ensure that the contractor is doing everything that the government thinks he's doing. And so there's also will be in the systems engineering method, you want to talk about how you're going to integrate the equipment, the systems. You want to identify if you're going to do what's called independent validation and verification of the system or the software. All that would be defined in here. To talk about your maintenance plan and if there's going to be any upgrades. So these are the kind of buzzwords that will float throughout the systems engineering methodology that you'll be hearing about. And some of you may have heard of these, and some of you will get to hear about this kind of stuff. But these are the kind of buzzwords that both the contractor will be using as well as the customer. This is a diagram showing, in general, the systems engineering method. And beginning here with some initial assessment, now, let me tell you, I haven't been able to find two references with the same systems engineering process defined. Different terminology, different flows, and so the systems engineering method has been, over the last 50 years, has been changed greatly by different companies for different reasons. And so I just want they use different terminology. In this case, under the feasibility study, they show it coming out of the system definition part, and where you might do your risk analysis and do some impact analysis. You might be doing some trade studies. But in this particular process that was used for this particular system, it's the overall general flow pretty much matches with the one I just went over. And so here's under the requirements gathering, doing some requirements analysis. Sometimes you may have a requirement, and when you analyze that requirement, you may not be able to do it. The technology may not be available, and so it may not be feasible to do, and that's done in the requirements analysis. And again, back to this systems partitioning or the allocation of the requirements, all drive to the systems design. Again, the system specs, you got your software system specs and development, system integration, all the same kind of thing. So there's kind of a natural flow when you've been exposed to it and you actually implement it, that you can go back to and say, oh yeah, that kind of makes sense. Yeah, we need to do a feasibility study before we start doing requirements to make sure that this thing is even possible to do, okay? There are a lot of ideas that people come up with that aren't feasible. That's why we have to do a feasibility study. Great ideas, we're just not ready to do it. So here are some examples of what a requirements traceability matrix may look like. Just shows a list of the requirements and then where you would go in the documentation to find more information out about it. So that's a very simple traceability matrix. This would be the cover page of the Phase A study. It could be 2 pages long, it could be 1,000 pages long for the Phase A study. And then the Phase B study would look a lot like the Phase A study, but hopefully it would be more detail. If you might be able to get if you're buying communications equipment. In the Phase A study, you might get a photograph of what it looks like. In the Phase B study, you might get the link analysis that proves that piece of communications equipment will actually close the link and you'll be able to communicate with your buddies out on the field. And so that was what a Phase B study would look like. And so the ops concept I mentioned, where before anything any requirements can flow, you've got to have an ops concept written. This one happens to be for the space-based infrared system that's being used with a satellite up in space, and they're trying to catch ICBMs as they're launched by the enemy. So there was an ops concept that was written that said how the space segment was going to talk to the ground segment folks and make sure that if there's any ICBMs that go off anywhere around the world, this system is going to catch it and then relay that information to the right places. Any questions or comments? Have I offended anybody yet? Okay, there's still time. Here's a couple of more products of the systems engineering method for the again for the SBIRs, the space-based looking at trying to catch ICBMs as they get launched from any place on the Earth. You know, this would be pertinent to Israel, right, or to Iran right now, where we're all concerned about someday them launching some ICBMs at Israel. So this would be a system definition chart for the SBIRs program, and then this would be, you know, a program plan. Talking about the existing system is called the DSP, the Defense Support Program. That's been looking at catching ICBM launches for the last 50 or 60 years, and how it's going to migrate into the latest one being done by the spacecraft is being built by Lockheed Martin over here in Sunnyvale. And anyway, this is going to be the program plan of how it's going to integrate the total system. That's going to come out of the systems engineering method. Now, the systems engineering process that I alluded to earlier is different than the method in that a process, you have inputs into the, if this was the process, you have inputs into a process and you have outputs into the process. And what goes on in here within the process can vary. It's not an order, it is a uniquely ordered process, but it doesn't have to be repeatable or repeated. The systems engineering method flow is somewhat fixed. You don't have inputs and you don't have outputs, and then the process in the middle where you manipulate the data to get the outputs. So when you talk about the systems engineering process, you're talking about the customer. The government quite often wants to know, when a company builds something, what is the process that they use to come up with the product that they're building. And so the contractor's got to come up with his process. He's got to tell the customer what data did he put into the process, what is the order of things in which he did things in terms of avionics equipment, how they were built, how they were assembled, where the requirements came from. All that's got to be told in the process, and then the output of the process here might be all of the documentation that I was talking about earlier. So the systems engineering process is different than the systems engineering method, and sometimes you hear them used interchangeably, but they're different. And so who uses the systems engineering method? Well, big organizations quite often, like the US government, DoD, NASA, JASDA, the Japanese version of NASA, Intelsat, Iridium. Iridium and Globalstar are the two space-based telephone networks where you can use one of their telephones and talk with anybody all over the world. It routes up to a satellite and then down to whoever you want to talk to, versus using the telephone network or the internet. So both Iridium and Globalstar. And what they do is they put out an RFP that says to the companies, we want you to use the systems engineering method to come up with what you think we need for a space-based telephone system. And then the companies will do it. So the DoD does it all the time. They want the people that are going to be building their satellites to understand the systems engineering method, how the whole system is put together, even though they're only going to be responsible for building one small part of the system. The government quite often wants each company to have systems engineers on board. But as I mentioned earlier, the people who bend metal don't want to push paper, and they're quite often offended and just simply won't do it. And so companies that actually build and produce stuff will often only hire systems engineers when they're ordered to by their customer, and then once their customer's gone, the systems engineers have to find new work somewhere else. So there's a big difference in the skill set needed by the systems engineer versus the subsystems engineer or the RF engineer or the guy that specializes in a particular field. So I use the systems engineering method to design and develop and build what's called a mobile, modular, survivable shelter. And what this did was provided all of the equipment necessary to operate the Air Force's space-based assets for warfighting. And back in the 80s, the military decided that a nuclear war could be survivable, so we needed to have reconstitutable assets. And so what they decided to do was, for their ground stations that they talk to with their satellites, make them mobile and then survivable. And so we designed this to be able to sustain a nuclear bomb within a 100-mile radius. And what this is, everything in here is the equipment that is used for communicating with the satellites, making sure that it would work after a protracted nuclear war. The assumption was that the equipment during a 6-month nuclear war we wouldn't be able to talk to for a variety of reasons. But after that period, we would want to be able to reconstitute all of our military assets. And so I worked on developing this, and I'll show you some details about it in a minute. But again, the ops concept for this vehicle was to provide all spacecraft mission control, TT&C, telemetry, tracking, and commanding services for all of the Air Force satellites that were, at the time it included the ICBM launching the DSP program, GPS satellites, the Navy's FleetCom communication satellites, and the low Earth orbiting satellites that provided weather data. And so all of those needed to be reconstituted if there was ever a nuclear war. And this was the kind of equipment that was going to do it. And notice that it looks like a very commercial truck. And the goal of that was so that it could hide in plain sight. It was mobile, survivable, and it just looked like any other plane, a semi. And so at the same time that I designed this 50-foot van and semi-truck to do a ground station, this is what NASA's mobile ground station looked like at the same time. All these trucks and vans and all this construction equipment. This truck, all the equipment on this in this 50-foot van did everything that all this equipment was needed to do for NASA. So you can see NASA was a lot behind the times compared to where the military was thinking, in the 80s. And this, by the way, was a NASA JPL down here in Pasadena. This was their mobile tracking station. And it was designed without a systems engineering method, and it did virtually the same thing as the 50-foot van. So here are some of the parts that were included in that 50-foot van. This is a electronically steerable phased array where this is a flat, this was on the top of the truck. This was the transmit and receive antenna that was used to communicate with satellites overhead. And it was the first time that the array of so large was ever produced. This was back in the early 80s. Very common now. Very, very, very common now, but in the 80s it was, this was one of the very first early ones that sat on the top of the truck. And so this one was to communicate with most of the military satellites, GPS, DSP, DMSP, and the Navy's UFO. And so this would have been the communications equipment necessary to communicate with the military survivable communication satellites. At the time, I think they were called MILSTAR. Today, they're called AEHF. And then this was the UHF antenna that was going to command and control all of the Navy satellites. And all this equipment was embedded in that semi-truck that I showed earlier. And so this was, the NASA kind of paradigm of a mobile transportable ground station. And then this is what the inside of the 50-foot truck looked like. So what this says is that from the early days of the 60s and 70s, a great deal of miniaturization was done by companies. And so much so that we could put everything that we needed on inside of a 50-foot van. And this is kind of like what it looked like. And then have two people, drive around the van. It included enough food supplies for like 6 months. Everything that two men needed to survive a chemical, a biological, or a nuclear war was in this van. And so this kind of gave you an idea of how much equipment was in there. But thanks to the miniaturization that was done by industry over the decades, that's what really allowed us to come up with such a small van. A survivable van. Now remember, I said this would survive a nuclear bomb up to 100 miles away and still function. So this is what the cab looked like, what a cab would look like for the two people, for the two drivers that we could convince to stay inside and drive around. So they seem to have a lot of living space. So some pros and cons about the systems engineering method. Any questions or concerns or Any insults yet that I need to apologize for? Okay, so for some good things about the systems engineering method, both the customer and the contractor can use it, so nobody's got an advantage. The government, one of the other benefits of the SEM, system engineering method, it allows companies who has never built something to provide a bid to the customer. And it opens the field for the number of bidders on contracts. Because if there's a standard approach, the company who has done it before doesn't have as much advantage over companies who've never done it before. And that's a good thing for the customer, to have the most bidders possible, because quite often it affects the price, affects the quality. Everything is affected by the more bidders that you have. And that's one of the great benefits of the systems engineering method. It allowed companies with absolutely no experience, companies that build ships, they could bid on building satellites or a rocket by using the systems engineering method. It allowed them to do so. So it takes an engineering effort from an idea to an actual product for delivery. It's been the best tool for planning major and minor design and manufacturing efforts. The biggest thing it does is it ensures that whatever the contractor makes actually matches with what the customer asked for. That's really the big thing. Because when you have a multi-year projects and people transfer and go, quite often a lot goes with those people. And so there has to be some way of ensuring that whatever gets delivered to the customer is what the customer asked for. And that's what this does. So it documents all decision making, provides full traceability of all actions taken during the program. It's adaptable for small projects, but it's highly expensive. You got to have the funding available. It's a major effort to do the systems engineering method, not usually used on small projects unless you got a lot of money, because it requires a lot of people and paper. There's many commercial systems engineering methodology tools available in software that helps you do all of these things. It will generate formats for you. It will generate your ops concept. It will generate all your requirements, documents. It will do it all automatically for you. So it's very convenient. And in the event there's a conflict between what the contractor says, actually delivers, and what the customer says, it provides really the evidence that shows whether or not the requirements were adhered to by the customer. Now, the things that's not so hot about the systems engineering method. Did anybody have any other pros besides what I identified? The things that are sort of negative about the systems engineering method is it's very labor intensive, expensive because you've got a lot of people pushing a lot of paper around and generating a lot of information and documenting it and making sure that everything's current and up to date. Very, very complex. As I say, overly complex. It must be used in a highly controlled environment in order to be accurate. And it's difficult to keep the contractor maintaining all that documentation, because contractors quite often want to bend metal. They want to make stuff. They don't want to generate reports. And so if they've got a choice of building something, producing something, and generating a document for your systems engineering methodology, they're going to pick bending metal every time. And so that's what it really requires a lot of effort to keep the contractor maintaining the documentation that's created in the systems engineering method. As I mentioned before, requires different technical personnel to generate and maintain the systems engineering method over those that actually bend hardware. And probably the biggest flaw is that the most negative thing that occurs on big programs is what? Cost overruns and schedule overruns that are no accident. They occur because the customers decided they want more things done, and that means more requirements. The systems, and that's called requirements creep. Is anybody familiar with that term, requirements creep? Yeah. The systems engineering method was never designed to handle requirements creep. We use the SEM on almost everything, and then as we get into a project and you find out, gee, it's only a few more dollars and you get all this more capability, don't you want to do it? And the customer will often say yes. As an example, the weathers at night, the weather pictures that you see on the news were a picture of the Earth and the Earth's weather. NASA some of those satellites were built the contract was won in 1983. ITT, the builder of the cameras that take the pictures, they told NASA, if you wait 6 months, we can double the aperture of your camera. 9 years later, the contractor was done, doubling the size of the aperture. Okay, promised 6 months, 9 years later. And so, I forgot my point.
Requirements creep.
Oh, requirements creep. That was an example of requirements creep. And 9 years later, the contractor had to go back and use the manufacturing standards from 9 years before in order to produce these satellites. So the systems engineering method was not designed to handle requirements creep. And now I haven't been to school in a long time in systems engineering, and that may not be true anymore. I don't know if they've ever tried to adjust the systems engineering method to handle requirements creep, but the requirements creep is a great thing. It allows capabilities to be added to systems, usually for just a few dollars more, that nobody ever thought of at the start of a program. But yet it gets a lot of bad press and actually can end programs because of cost overruns and schedule overruns that a lot of people don't like. And so programs that I've used the systems engineering method on included the mobile survivable ground support, the semi-truck, the Japanese government's geostationary meteorological satellite system, Nippon Telephone and Telegraph, a private company like AT&T, they got their own satellites, the Air Force's DMSP, low Earth orbiting weather satellites. They wanted the systems engineering method used on the Block 6 program, which eventually became the NPOS, or the National Polar Orbiting Environmental Satellite System, the one that's kind of tracking global warming and all that stuff. That was originally Block 6 DMSP, and now it's taken over by NASA, and it's a giant science fair. Also, the NASA Space Station Freedom used it. Programs that I did not use the SEM on, as the GPS Space and Ground Segment Manager for the Block 1, Block 2, and 2A satellites. We were just given the requirements, what to do, that came out of the systems engineering method that I think Aerospace Corporation did. Okay, we just took the requirements and built a bunch of satellites. Same things with the Superbird commercial communication satellite, Anik E2 Canadian communication satellite, the NASA ColdSat. Again, the NASA's version of this is the satellite that I told you about on requirements creep, where the aperture was supposed to double in 6 months, and it took them 9 years. And then 12 Intelsat communication satellites. So these are programs that we were just given the requirements that came out of the SEM to go off and build.
So basically you had a mixed bag on the ones that didn't use the SEM.
Yes.
It wasn't
Yes,
a matter of all of the ones on the left weren't grand successes.
No.
They had their problems.
They had their problems, yeah.
They had cost overruns and that.
Yeah.
But how would you compare overall the ones on the left to the ones on the right? I mean, is there any difference? I mean, there are different kinds of programs.
Well, what happened here was they were looking up front for a concept definition. They said, we've been doing this for a while already, but maybe the technology has changed so much that we can do a whole lot more, or we can add more features and that kind of. And so they were willing to spend a lot more money to look and see if they could make big changes that would give them benefits. These folks were willing to do that. These folks said, we've already done that, just build it for us. That's all. We've already done that analysis, just go ahead and build it. Here's the requirements, boom, go. And all I'm doing, I'm just pointing out my personal experience on these programs. We did the system concept, we did the feasibility study, the concept of operations, all the phase A, phase B study on these programs that these customers were willing to pay for. In this case, these customers were not willing to pay for it. They didn't want us to bother with it because somebody somewhere magically had already done it.
Okay.
Yeah. And so I mentioned about how we were able to miniaturize all of the TT&C equipment and put it into a 50-foot van. In 1997, when I was working at L3 Communications, I was able to take that 50-foot van and stick it into a 21-slot rack-mount PC tower. The companies had miniaturized all of the equipment that it took to do satellite command and control from the early 50s and 60s, where it took 4 or 5 or 6 or 8, 10 vans of equipment, and often tube-based equipment, miniaturized it, and allowed me to shrink it down. All that 50-foot van, the TT&C services could be done for all of the military satellites, all of the commercial satellites, and all of the military secure satellites out of a 21-slot PC rack mount unit. And so I was fortunate enough to be able to do that in 1998, and it's still sold today by L3 Communications. I think it's called, I think they call it Vista. So you got these people here looking at the data coming from they're either sending commands up to satellites and receiving data back from the satellites, as well as receiving the tracking information that says how fast the satellites are moving, either towards you or away from you, kind of thing. But all those vans of equipment were shrunk down into, I mean, to me, it's just amazing. Shrunk down to a little 21-slot PC. I could have put it on a desktop tower, but they wanted me to make it look more industrial, and so I forgot to mention how much I charged. $75,000 for a 21-slot, and they wanted it in a rack. So it looked like there was more to it than just 21 slot. But for $75K, we could deliver something that would have cost $100 million 30 years before. It wasn't. I didn't do the miniaturization. This was all done by industry out there. All I did was pull all the pieces together. So in conclusion, any comments or questions before I conclude? The SEM was developed to take the design responsibilities of large complex systems away from the contractors and give it to the customers, particularly DoD and NASA. It's a useful, reliable, and complex tool that ensures the end product matches the product that was first purchased and desired. Using a SEM, systems engineering method, is expensive and labor intensive. The companies, not all companies use systems engineering method. Particularly the ones that build big, complex systems, because, again, it requires a different skill set. And it's used by customers that purchase large, complex systems. And as I said earlier, it may fail to address the requirements creep and how to make sure that when you have requirements creep, how do you make sure that what's finally delivered matched with what you started with, plus all the additional requirements. That concludes my discussion. Any?
An awful lot of data there. Does anybody have any questions or comments at this point?
Is it different than anything that you've heard in any of your classes?
Oh, yeah. I can tell you that. It'll be different than what they'll be hearing.
Okay.
Sure.
That's what I was wondering if
Let
anybody...
me point out, just let me make a couple of comments. First, this ability to not address requirements creep. Requirements creep is a tremendous issue. It comes in all the time. There are many ways to look at requirements creep. You mentioned that in some cases it's good to have a lot more performance for what nominally starts off as a little bit more money and time, although sometimes it turns into a lot of money.
A lot of money and a lot of time.
But let me give you two examples of ship programs that have had requirements creep. And again, I'm stretching the semantics here. On the Aegis program, we started off building cruisers that had a Mark 26 launcher. Any of you familiar with Mark 26, the rail launcher?
The Bandit.
The what?
Double Arm Bandit.
The double arm Bandit, yes, absolutely. And then along comes the vertical launch system. Well, it's a lot better. Let's put the vertical launch system on the Aegis cruiser. We've got the Aegis radar. All we need to do is get rid of that double arm Bandit and put this nice block of missiles on the cruiser. Now, is that requirements creep? We've got a lot better system coming down the pike. Why don't we just change the approach we're using? You might say that was requirements creep, but what happened, interestingly, on that program that's different from another program I'm going to cite right away is the fact that set of requirements creep was turned in to another flight, to another block of the ship. And it was done in such a manner that Congress, the public, the Navy, the contractor, everybody ended up making it happen without a tremendous uproar. And, by the way, it cost a lot of money. But it was planned. It was planned. We're going to do this. We're going to build 5 of these ships with the Mark 26, and then we're going to build the rest with this vertical launcher. And we know that's going to cost more, and we know that's going to require more time, and it's going to require more engineering and the whole 9 yards. But we want to do this, and so we're going to allocate the money to do this, and it was done. Contractor did it, the Navy did it. We went out and built the next flight of ships with the vertical launch system. So that's a case where you might say that requirements creep was handled in a very effective manner by planning. And it didn't look like requirements creep. Now we'll go to another instance. The LCS. The LCS, as everybody knows, has really expanded in terms of delays and amount of money cost to build the LCS. And one of the big issues that the Navy and the contractor has pointed to for the reason for this is requirements creep. The Navy initially said, we want you to build this ship to commercial standards. And then they thought about it for a while and they said, oh my God, no, we can't build it to commercial standards. We need to build it to shock standards and military standards, and we got to change that. So they did. That caused a tremendous problem. And the contractor was able to say on his part, well, you know, all these delays I'm having and all this additional money that I need to build a ship is because you come and change the requirements on me. And I claim, had they wanted to do that, and had they done it using the same model that they used for the Aegis cruiser, you wouldn't have had the problem. You might have built 2 or 3 ships to the commercial standards, or 1 ship to the commercial standard, and then said, okay, now we want you to rebid this contract, and we're going to go back and we're going to tell the Navy, we're going to tell Congress and tell everybody else, we've got a different ship here. We've got a ship that's now built to military standards as opposed to commercial standards. So I give you this example to talk about requirements creep. Be careful in your own careers when it comes to, when the contractor comes to you and says, you know, I can really improve the performance, and I can do it in 6 months, or I can do it in a year, or whatever. Understand that what you're going to have to perhaps pay in terms of schedule and dollars for that improved performance, and do it in a structured way. Do it in a planned way. And it goes from being requirements creep with overruns and delays to a phased program that has blocked upgrades. Okay, any questions? Have any of you seen any of the material that he's presented in your classes so far? You have? Okay, so you begin to see. There are variations in what he says, what he said today, and what you're going to be getting. That's okay, and the place to discuss that is with your professors and see what they say about it. I mean, I can go into some of the points that he's made and we can have a discussion on it. We're not going to do that for the sake of time, but if you have any questions, if you have any particular issues with anything, come and see me and we'll talk about it. Okay? No questions then? Thank you very much.